What if mass doesn't come from a field at all, but from the shape of space itself? For decades, physics has treated spacetime as a passive stage where particles and forces play out their roles. But a growing body of theoretical work suggests something far more radical. Spacetime itself may be the source of those particles and forces. New research proposes that the fundamental behavior of nature could emerge directly from geometry. In other words, the structure of space may not just host physics, it may be physics. In a paper published in Nuclear Physics B, physicist Richard Pinchak and his collaborators explore whether matter, forces, and even mass could arise from hidden dimensions beyond the three we experience every day. Their idea builds on the possibility that our universe contains extra dimensions that are tightly compacted and invisible to us. These dimensions may form complex seven-dimensional shapes known as G2 manifolds. Traditionally, physicists assumed these shapes were static and unchanging. But this new work asks a different question. What happens if these hidden geometries are allowed to evolve over time? Using a mathematical process called the G2 Ricci flow, the researchers modeled how these extra dimensions slowly reshape themselves. Crucially, these geometries can possess something called torsion, a built-in twist, similar to how DNA coils or how certain molecules have a natural handedness. This twist changes everything. As the geometry evolves, the team found that it can naturally settle into stable, self-sustaining structures known as solitons. These solitons emerge purely from geometry without requiring any additional physical fields. According to Pinchak, this could provide a geometric explanation for spontaneous symmetry breaking, one of the key processes that shapes the laws of physics. This leads to a bold reinterpretation of mass itself. In the standard model, particles gain mass by interacting with the Higgs field. But in this new framework, mass may arise from resistance within geometry. Instead of particles acquiring weight from an external field, they gain mass because twisted spacetime resists change. As Pinchak puts it, matter emerges from the response of geometry to its own internal structure. The implications don't stop there. The researchers also link geometric torsion to spacetime curvature on cosmic scales. This connection could help explain the positive cosmological constant, the mysterious driver behind the universe's accelerating expansion. They even speculate about a new particle associated with torsion, tentatively named the torstone. If such a particle exists, it could leave detectable signatures in future experiments. Ultimately, this work extends Einstein's original vision. If gravity arises from geometry, why not mass and the other fundamental forces as well? Nature often favors simplicity, and it's possible that the weight of the universe comes not from a field added to space, but from the hidden twists of space itself.